So we're doing English, right?
Yes.
Okay. So, I'll talk about phase retrieval, as you said. I'll start with a little bit of background about myself, though, just for a few slides. So in general, I'm an applied mathematician. I do things as a very broad umbrella term. I do things related to theory and algorithms, theory of existing algorithms or theory for developing new algorithms. The theory part is sort of related to optimization, discrete differential geometry, or functional analysis. And the algorithms come from applications in 3D computer vision or graphics, and biological applications and machine learning. That's sort of the general kind of thing. And a little bit more in detail things I'm actually working on. So sort of in my early history, so to speak, in my doctorate, a lot of the things I worked on are related to geometry plus optimization. I'm still working on this kind of thing now. So as a theme, this means, that they're trying to compute some sort of a geometric object, which as a geometric object is pretty well understood. And there are some reasons to want to compute it application-wise. And the question of how to compute it, though, is an interesting question. So for example, this is my first project in my doctorate, was computing regular homotopes between curves. So you're given two curves and you want to interpolate between them and preserve their topology. Something that I have worked on in the past and now I'm working on again is topologically correct surface reconstruction. You have some sort of 3D model of data, which is noisy, and you want to reconstruct from it a clean model of your object, and you know what the topology should be. So for example, if it's a brain, you want it to be a genus zero surface, or if it's roots of a plant like you see here, you think of it as a graph, so that graph should be a tree. So that kind of thing. Another thing, conformal mappings, how to compute them, which is, again, angle preserving mapping are something that people want to compute. And I talked about this in Bar-Ilan 2 years ago or so in some seminar. And finally, computing isometries, which is also an important problem, a problem I worked on a lot, which is where you have, say, two 3D models, which are pretty similar, but they may have very different postures, and you want to compute the correspondence between them, which you can do using isometry. So anyway, that's one kind of thing. In my postdoc, I've also sort of branched out to two sort of different type things. One is approximation power of deep neural networks. So I think, well, I don't know if well known, not well known. In general, deep neural networks are very useful in the last few years. The sort of classical example of what they do is you take an image and you have this semantic function which says what's inside the image. So for people, that's a very easy function we know how to do that, but we want to teach a computer how to compute this function. And deep neural networks are the idea of doing this searching inside a very specific hypothesis class, which is functions which are compositions of simple functions, usually a linear function composed with a fixed pointwise nonlinear function. And this works very well. And so from an approximation point of view, people are interested in understanding why hypothesis classes, which sort of vaguely look like this, are better than what we used to use, in the past, or still use in the present sometimes. So one example of such a result, which is in our paper, is depth separation for fractals. So we show that you can sort of, because fractals are built in a recursive way, you can, let's say something like the Sierpinski triangle, which at iteration k has 3 to the power of k triangles, you can compute with a neural network using only a linear amount of parameters in k. So you can compute them very efficiently when the network is deep. So that's why it's called depth separation. For a shallow network, it won't work. And Boris is related to, we spoke about, so this was somewhat related to what I did in the master's thesis with Mike at the time. But anyway, so that was that. And another kind of thing related to approximation power of networks is working on universality for invariant networks. So this is not talking about why neural networks are better than other models in approximating function, but just showing that for specific kinds of networks, you still have the universality property. They can approximate any function. Okay, so what is this kind of network? So you have, so sometimes you want to build neural networks to respect the invariances of your objects you're working with. So for example, sometimes instead of images, you have a 3D point cloud. So you have let's say this chair represented by endpoints in R3. And you want to solve the same problem as before. You want to have a neural network that will learn how to represent this function that says this is a chair. And then variances are that if I rotate or translate the chair, but also if I relabel the points, then it will still be the same chair, right? And therefore, what you want to do and what people have suggested is to build your networks, your family of functions you want to learn from in a way that are built in invariant to these symmetry, rigid motions and permutations. And then once you build sort of these specific networks, then the question of universality comes up again. And what we recently showed is you can, with these constructions, still approximate all continuous functions which are invariant to these symmetries. So that's sort of two different kinds of things I've been working on. What I want to talk about today is this third topic, which is phase retrieval, which is also a bit new to me. I've been working on this for the past year. And okay, so this is where the talk really starts, and please ask questions as much as possible. So phase retrieval, what is it? So we have the input is a signal in some Hilbert space, or sometimes it's not a Hilbert space, a Banach space or something, but let's say Hilbert space for convenience. And what we're given is, we don't know the signal itself. We're given linear measurements of the signal, and but we lose the phase of the linear measurements. And then the question is whether we can invert this process. So can we, can we from these phaseless linear measurements reconstruct the signal? And this is a problem with applications in various fields. So it comes out somehow in many things. For example, usually in these fields, the linear measurements are specifically the Fourier transform or the windowed Fourier transform, but sometimes there's something else. Here's an example where this happens with the windowed Fourier transform. This is called tychography. So in tychography, what happens is you have some specimen you want to measure in sort of small thing in nanoscale. So let's say this is a slide which contains biological cells or semiconductors or something or other. And you point some electron beam or X-ray beam or some kind of beam at the specimen, and you get a diffraction pattern. And this sort of somehow corresponds to taking linear measurements and only keeping the phase. Specifically, what happens in tychography is you do this in small sort of windows, overlapping windows. And then at the end of the day, you get this sort of picture where you have different measurements at different windows, and hence this is sort of corresponds to the window Fourier transform. Okay, so that's the kind of application. And again, since this is a very well studied subject, there's also a lot of research and from various different angles. So there could be engineers, computer scientists, mathematicians, and they research different things. So from sort of the more applied part, people usually are interested in algorithms, naturally. For example, this is a very popular algorithm to this day from the 70s, at least the idea.
Sorry, Nadav, can I interrupt? What does tychography actually mean? What is that word?
Tychography, what does it mean?
Yeah.
I don't know. To me, it means this imaging technique. I don't know what the Greek.
Oh, you don't know why it's called that. Okay. All right. Sorry.
As I recall, it says in Wikipedia, but I forgot what it says.
Okay, I'll go and look.
Easy to look up.
All right.
Yeah. Right. So the kind of things people research are algorithms, and also, on the other hand, I think more in the last, let's say, 15 years or so, there's a lot of interest in the more theoretical side, and that also branches out into two kind of things. One aspect is just to make algorithms with guarantees. So if For a more applied person, the way to check if an algorithm works is to check if it works. Then for a mathematician, the way to check if the algorithm works is to prove that it works. So there's papers like that. I think this is the most well-known theoretical paper on phase retrieval is this paper by Emmanuel Candes. And on the other hand, there's also research on this just as an inverse problem. So what is, is this process injective, or in other words, is there a unique solution, and is it stable, and is the inverse problem stable? So, and this thing is what we're going to be focusing on today. Okay, so what do we know about this? This is what I'm gonna, in the next few slides, I'm gonna talk about, whether this problem is stable and injective, and then talk a little bit in more detail about what we are doing exactly in that world. And to do that, we have to introduce some notation. So, okay, so remember that capital phi is a collection of measurements, finite or infinite. So it's a set, but it's also convenient to use this notation where phi of f signifies the sequence generated by these measures. And also we have this notation, which means that you take the magnitude of all, the vector of phi f, and you take the magnitude of each one of its entries. Okay, so that makes life easier. Another thing that we need to know is that when we talk about injectivity or phase retrieval in general, it's only up to global phase. So if I have a signal f or a signal minus f, and I take a linear measurement and I take the magnitude, then the measurements will all be the same, right? So I don't have really any chance of distinguishing f from minus f. And therefore, when we're talking about real phase retrieval, where our signal is coming from a Hilbert space over the reals, then we're really talking about phase retrieval in this quotient space. And in complex phase retrieval, similarly, we're talking about this quotient space, H over S1. Okay, so that's, when we say injective, which is what we're gonna be talking about now, that's what we mean. So we mean up to this global phase ambiguity, which we cannot resolve, is this mapping that takes a signal to the linear measurements and then takes the magnitude, is that injective? Which is, of course, I mean, if we want to have any hope of reconstructing the signal, it will have to be injective. Okay, and it turns out, I don't know, in a way, I mean, you could think, maybe not, because you are losing information, but it turns out that the answer is often yes. So for example, if you have a finite dimensional Hilbert space, an RD over R, and then you have, you take a random choice of 2D minus 1 measurements. So that gives you basically a matrix in R 2D minus 1 times D, right? So 2D minus 1 vectors in RD. So almost every such choice with respect to the Lebesgue measure will give you injectivity. So that's good news. And in the complex case, it's a little bit harder to prove, but it's still true. But just instead of this factor of 2, you need to have a factor of 4. So you need 4 times as much measurements to get your result. And additionally, if you're saying, okay, what about infinite dimensional Hilbert spaces? So yes, we also have results about that. So for real band limited signals, you sample them twice more than the Nyquist rate, then you have injectivity, which is it's really the analog of this result, because the Nyquist rate is what you would need to reconstruct the signal if you could keep the phase. And therefore, if you do twice as much, that's sort of corresponds to doing 2D measurements in RD. Okay, and also in the complex case, again, also there's some sort of similar results, although they're a little bit less clean because it's not for all signals, it's for almost all signals. But there's sort of, in general, there are, the picture is that we know injectivity can happen and often happens, but it does depend on the specific model, what the measurements are, etc. And if we manage to prove it yet or not. Moving on to stability, right? So stability is saying, let's say we have injectivity. So in theory, there is a unique solution, but how difficult will it be to find it? And we measure this through this inequality, where on the left-hand side, there's sort of the natural distance in the quotient space, right? So you compare F and G in the Hilbert space, but you allow global phase to make them as close as possible as they want. And on the right-hand side, you have sort of a distance which you get from taking the measurements, the magnitude of the measurements. And the question is whether there exists some sort of Lipschitz constant here and how big it is, right? We call this the stability constant. Okay, so that's stability. Do we have stability? So first people said yes, because in finite dimensions, if you, let's say we proved that there is injectivity, then that automatically implies stability, meaning that there is some constancy smaller than infinity for which that inequality holds. However, this constant, it turns out that it suffers from the cursive dimensionality. So what does this mean? First of all, in infinite dimensions, there's never stability. There's no way to get stability ever. And also, the stability constant can grow exponentially in the dimensions. So in sort of, in specific examples, but which seem pretty natural, you can take finite dimensional spaces, and as you increase the dimension of the space, the stability constant grows very, very fast. So that seems to indicate that maybe we have some issues with stability. Okay, and what are these issues? So people observe that these issues are usually used to due to some sort of disconnectedness. So what does this mean? Here's an example. So say you have a sum of two Gaussians, or the difference between two Gaussians, and they're concentrated far away from each other, right? So let's say the orange signal here is the difference, right? And now we want to measure, let's say our measurements are pointwise. We just measure at a certain point. And we want to see how, if we can do phase retrieval, we should be able to differentiate between the orange signal and the blue signal. But that will be rather difficult because, if you look at the value here and you only get the magnitude, how different will it be from the value here? It's hardly any difference, right? The only difference is that the Gaussian that's far away contributes differently. But that's, it's very negligible. So that's sort of the reason for it. Usually when people give an example of where the stability sort of, I'm looking for a word that's not a curse word, is wrong, F's up, then the reason is usually because of this kind of problem. And people have taken this observation in different directions. Specifically last year, there was a very nice idea of how to use this in the constants, in the context of stability specifically, which is saying as follows. Let's sort of measure stability via connectivity. So instead of having our definition of stability before, which was uniform in F and G, we have a different definition where we're saying, let's look at a specific signal. We're not going to say something about all signals. Given a specific signal, how easy will it be to reconstruct this signal? So we allow a constant which depends on F. And this constant should measure how connected, in a sense, F is in the measurement space. So for example, if we have this sum of the Gaussians that are very far away, so this constant should be very, very, very large. But if we have some signal that's concentrated well in sort of the same area, then this constant should be good. And that way we can at least, given a signal, measure how difficult it will be to do that. Okay, so that was an idea. And of course, in the paper, they just didn't just tell us about this idea, they also actually achieved this idea. And I'll tell you in one slide what they did, and then I'm going to do it again in a different way. So so what did they do and why do I want to do it again? Okay, so they did this specifically for Gabor phase retrieval. So this means it's a windowed Fourier transform with a Gaussian window. Okay, so we have our signal F, which is, let's say, a one-dimensional signal. And we multiply it by some window at a point X. So that gives us something concentrated around X, the Gaussian window in this case. And then we do the Fourier transform of that. And for this type of measurements, they achieve phase retrieval. Disadvantages of this, which is why I want to do this again, is that they use a continuum of measurements. So the measurements are, for every X, Y in R2, these are the measurements you get, and using that, you can do stable reconstruction up to this connectivity. But that's way too much, because what we want is, we assume that we need like 4 times the Nyquist rate or something like that. We don't want the continuum. And also related to that is that their proof relies on elasticity of this function. So it's a function from R2 to R2, and it's analytic, and it's not really analytic, but you can multiply it by some weight function and it becomes analytic. And that was very helpful for the proof, but it sort of seems also, besides the fact that we want to do discrete and then this won't work, this also seems to be not an essential property of the problem, because, if the window is, maybe it's not smooth, but it's still, so it should still work if the window is not smooth and it's not specifically a Gaussian, maybe it's some other smooth function even, should still work. So it seems like there's some more things to learn about this. And so hence, what I want to talk about is this project we have, which we could call phase retrieval and graph connectivity, which is doing the same thing, but in the discrete world. Okay, so the same kind of a result in the discrete world. The main results here are just, first of all, just achieving a discrete theory for this problem. And also a sort of interesting relation between real phase retrieval and the Tychography constant and complex phase retrieval and the algebraic connectivity. So the Tychography constant and algebraic connectivity are 2 different ways of measuring connectivity of a graph. And I will try to convince you that they are related to 2 different types of phase retrieval in a way. And also there's sort of concrete examples where we can understand whether indeed using this framework and only talking about connected signals, to what extent we really are avoiding the curse of dimensionality. Okay, so that's the paper. It's joined with Ingrid, with Jian Feng, and with Cheng, all who were at least in Duke. Cheng is now in China again. She's not that young. I think it's probably illegal to work with someone who looks as young as she's in the picture. She's young, but not that young. Anyway, okay. So let's get started talking about this. I would say the structure of the paper is, in general, that we introduce this LSCC measurement scheme, which is some, a collection of phase retrieval, discrete phase retrieval problems which we can work with. And then we prove some things about that, and we also branch out to 2 examples. But I think for the purpose of the talk, it will be useful to start with an example. I'm going to start with a finite dimensional phase retrieval model where I think it would be easier to sort of understand what's going on and what our definitions are, motivate the definitions, and then I'll go back to the general definitions, okay? So, by the way, questions up to now? Okay. Okay, so a finite dimensional windowed Fourier model. So we have, we're working in RD, or complex to the power of D, where D in this picture is 8, but usually will be much bigger. And we have a window. So the window will be of length 2a. Here 2a is 4. And the windows overlap at something of length a, okay? And, and the question we want to ask is, well, okay, the setup is as follows. So we're assuming we're given measurements on these windows. So we have a collection of measurements supported on this window, and then a collection of measurements supporting in all of the other windows. And for the sake of simplicity, we'll assume that each window on the Hilbert space it's supported on, it does phase retrieval stably with the same constant. So, okay, so let's say phi1 is supported on the first 4 coordinates, and as far as the first 4 coordinates are concerned, I can reconstruct them no problem. Okay, and then the question is whether I can, again, up to phase in this first 4 coordinates, then the question is whether I can get stability and invertibility for the union of all these measurements when I consider the sum of all the Hilbert spaces. Okay, so that's the setup. Again, in this example at least. And then what this is, once we build it in this way, this is basically reduced to a synchronization problem. So what does that mean? So, okay, we already know that we have phase retrieval perfectly on phi1, on H1 and on H2, for example. Okay, so in other words, this means that if I have two signals and I know that phi1 of f, the magnitude of phi1 of f is the same as phi1 of g, or the magnitude of phi2 of f is the same as phi2 of g, this means that if I project f onto the first space or the second space, and then it will be the same as g up to a phase factor. But these phase factors could be different, right? So if I project onto the first guy, there's some phase factor. If I project onto the second guy, there's some different phase factor. And so to get global phase retrievability, what you need is something to sort of stitch these two phases together. And that something is information on the overlap, right? So if your signal f is not completely zeroed on the overlap, then you will be able to stitch these things together and know that the phase is the same. So that's the general idea. So, and signals which will be problematic are signals for which you won't have this. The f3 squared plus f4 squared will be 0. Okay, so in general, you can encode this structure in a graph. So in this graph, each vertex corresponds to one of the measurements. And there's an edge connecting them if there's an overlap between them, which means that potentially we can stitch the phases together. And then, okay, that's a general, that doesn't depend on the signal yet. And then when you give me a specific signal f, then you define a weighted graph where the weights of the vertex are related to the measurements and the weights of the edges are related to the overlap. So for example, between 1 and 2, we have this f3 squared plus f4 squared we had before, which in our notation later, we will call this, this will be the norm of psi1 to f. So psi1 to f is a sort of linear measurements which are related to the edge, right? So specifically f3, f4, they're two measurements. Okay, and then, okay, so we have this weighted graph GF. And now the phase retrievability of f will be related to the connectivity of this graph. It's, for example, if I have f, which looks like this, so it's almost 0, it's 0 everywhere except for the first and fifth coordinate. So the corresponding graph will look like this. So since the first coordinate appears in phi1 and in phi4, there will be an edge which connects them. And since the fifth coordinate appears in phi2 and in phi3, there will be an edge that connects them, but there aren't any other edges. And so we get a graph that isn't connected. And indeed, this sort of corresponds to the fact that this function is indistinguishable from f hat, where you take 1 in the first coordinate and minus 1 in the last coordinate. So this sort of gives us a way of encoding in the structure when the phase retrievability via connectivity. Okay, so that's sort of the general structure in this example. And then if I move on to our general assumptions, then they are, do you want to vote? We can skip this actually. I don't know if, well, I don't know. So I'll give 2 slides about the general definitions. I don't know if they're helpful or maybe, if they're not, so forget about seeing them. In general, we're assuming we're given a graph, G, a Hilbert space H, and a measurement phi and psi, and they're related in the following way. Okay, so G is the graph. H is a sum of Hilbert's finite dimensional Hilbert spaces, HV, which are indexed by the vertices of the original graph. We also have the measurements, which are indexed by the vertices. So again, phi is a collection of measurements phi v. Each phi v is a finite collection of measurements. So it's sort of a sequence of sequences. And also we have a finite collection of linear measurements per edge, okay? And then our assumptions are related to how to tie these things together. So on the vertex level, we have the linear measurements phi v and the Hilbert space hv. And as we saw before, we're assuming that we can do phase retrieval stably there with a constant which doesn't depend on the vertex. We're also assuming this, okay, so which means that if I give you, okay, if I project onto composing the linear functions in phi v with the projection onto hv doesn't change the function, which means that if I get a signal f in the big Hilbert space, I can still reconstruct what happens in the hv specifically, because it sort of decomposes. So that's one assumption. And the second assumption on the edge level is that we have what we call conditional global connectivity. So that means that we have these psi UV, which are defined per edge, and they are sort of bounded by the measurements on each vertex separately, again, with a constant that doesn't depend on anything. So, okay, so that means that the measurements on the edges can be stably inferred from the vertices. That's also important just in terms of understanding what's going on here, because the phi's are the measurements I'm getting as a user. The psi's don't exist in the measurement scheme, like, you know, what's going on in practice, but it's something that I'm just gonna, you know, if you think of it application-wise, I'm gonna compute it from the other measurements. And I can do it well, sort of stable. And except for that, there are also some technical conditions that the graph is bounded degree, that phi is a frame, which means that if I didn't, if I could keep the magnitude, then I could do stable reconstruction, and that the norm, these norms are equivalent. Okay, so those are our assumptions. Now, again, given the assumptions, we have a graph induced from a signal. Okay, so if I have a signal F in our Hilbert space, and we have the structure of an LSTC measurement scheme, then I have a weighted graph, which I define by taking W of UV to be this, and the weight on vertices to be this, and then I take specifically the vertices and the weight and the edges in this graph are defined as the vertices and edges in the original graph, which have a positive weight. Okay, so that's the structure. And then what do we know about this structure? So preliminary result in a way is just to show that this is related to injectivity, which is, okay, the preposition says that if, at least in one direction, if the graph we build from a signal F is connected, then we will have injectivity. But that's not really our focus. What's more interesting is stability. Okay, so stability means, right, if we have, you know, how stable is phase retrieval for the signal F based on how connected the graph GF is. Okay, and here are our results, which I sort of mentioned before. So if you have a measurement scheme over the reals, then you have this this kind of stability constants where H of F is the Cheeger constant. And if you have a measurement scheme over the complex numbers, then you have a similar inequality, but where the constant here, instead of the Cheeger constant of the algebraic connectivity, the second eigenvalue of the equation. Okay, so those are the results. Now I want to devote some time now to explain, first of all, what the Cheeger constant and algebraic connectivity are. And, you know, assume maybe everyone knows, but if you want me to skip, let me know. But assuming that, you know, just to make sure everyone's on the same page, and explain why these things are related, and sort of tightness results, which suggest that really, you know, this, I mean, this just, so what I told you now just shows there's a proof that this works, but maybe someone else can prove it the other way around, right? Or with different constants. So showing that this is tight, okay? So first of all, what the Cheeger constant is. So it's, yeah, you are given a graph, you want to measure in a way how connected it is. Okay, so we do it as follows. This is the definition, but it includes in it some sub-definitions. So given a set of subset of vertices, the boundary of the set are all edges for which one vertex is inside the set and the other is not. So that's the boundary. And naturally, when you measure connectivity, you want this to be, I mean, well, you're not connected if this is small, right? So for example, if you are really disconnected, then you will have a non-trivial subset of the vertices for which the boundary is 0. Okay, and the size of the boundary is the sum over all edges in the boundary with the weights assigned to them. Okay, and on the bottom is sort of normalized by the size of the set of vertices. So the size is defined again via the weights of the vertices, and the idea why you normalize is that you want to, when you measure how connected the set is, so you know, it's easy to find a set with a small boundary if it only connects one vertex. So you want to, you know, you want to allow sort of compensate for that. Okay, And for example, let's compute the Chiro constant for this graph. It's a cyclic graph with 8 vertices. So let's say we specifically choose this partition S, which has 4 vertices here. Okay, so the boundary of this set will be just these 2 edges. And for example, the sake of simplicity, we'll assume that the weights on these edges is 1 and on the vertices is also 1. And so what you'd get over here would be that the boundary is 2 and the size of the set S is D over 2, right? It's 4 in this case. Right, and this is for a specific boundary, but actually this is the boundary which achieves the minimum. So that is the Chiro constant for a cyclic graph with D vertices. Okay, so that's the Chiro constant. Now, algebraic connectivity is something a little different. A different way of measuring, right? So you have the graph Laplacian. If you think of the graph Laplacian as a quadratic term, form, it looks like this. You take a vertex X, and you get this quadratic form, which basically is something that promotes smoothness in the sense that if you have 2 vertices, which are connected by a very strong edge with a big weight, so you won't want to get different values there, right? Specifically, the constant function, the most smooth function, is always in the null space of this operator, and therefore the first eigenvalue is always 0. The first is counting, all eigenvalues are positive, so we're counting bottom up. And then if a graph, a finite graph, is disconnected, then you will have lambda 2 equals 0. And in fact, the number of the rank of the null space is equal to the number of disconnected components. So based on this, it seems natural to sort of measure how connected a graph is in terms of how large lambda 2 is. So if it's 0, the graph is disconnected. If it's small, the graph is maybe almost disconnected. And so we have this notion of algebraic connectivity, which we can define in this way, right? So it's like what minimizes this term for all vertices, for all vectors which are orthogonal to the constant vector, which is always in the null space. And this definition, worth pointing out, is always valid even if the graph is actually not finite. So maybe there isn't a second eigenvalue, so this 2 is not exactly justified, but this definition on the right-hand side is justified. Okay, so that's algebraic connectivity. And how are these things related? So they're related through a sort of relatively well-known inequality called the Chigurh's inequality. So you can bound the algebraic connectivity from above and below by the Chiro constant. And this is a sort of useful fact also computationally, or at least in the sort of philosophy of computation. And it's used a lot for something called spectral clustering. And in general, the computational picture is, let's say you want to measure how connected a graph is. So computing the Chiro constant is NP hard. And computing, the second eigenvalue of a Laplacian is not hard. And so this sort of gives us an approximation of this quantity. So it's very useful. And it's very, here's an example of, maybe one of the first spectral clustering papers. It's very well known, and it shows, you have an image and you want to sort of break it up into the important parts or the disconnected components in a way. And you can do it using the spectral clustering technique. So somehow in spirit, using the second eigenvalue of the Laplacian. Okay, but in what our focus is actually is not on why these two constants are similar, but on why they are different. And I think in a way, the spectral clustering perspective in a way sort of dims that. But so at the end of the day, we have this inequality, and it does give us a bound from one direction to another, but still these numbers can be rather different, right? So it can be an order of magnitude different. It could be squared or not squared, right? And for example, in this graph we saw before, a cyclic graph with D vertices. So the Chigurh constant is proportional to 1 over D, right? We saw before, it's actually something like 4 over D. And the algebraic connectivity, turns out, is actually proportional to 1 over D squared. So there can be a big difference. They aren't the same thing. they're related, they're not the same. Okay, and so why? That's one point. Now, why are Cheever constant and real phase retrieval related at all? So I think you can sort of get, you can prove the theorem, but the intuition is, to me, is that, a Cheever constant is saying, let's go over all partitions, all subsets of the vertices, partition into two sets, S and the complement of S, and measure how connected that is. A real phase retrieval in our formulation is saying, for every vertex, we're going to choose a phase which is -1 or 1, and we're going to, and that's basically what's left to do, right? Because we're assuming that we do on each vertex, in a sense, phase retrieval works, and we only need to synchronize. So you can sort of see that there is a relationship, right? Because every vertex, every vector of this form corresponds to a partition over here. So the idea of the proof is to somehow connect these things first by doing Cauchy-Schwarz enough times and stuff like that. In contrast, when you think of the complex phase retrieval, so there you have to choose a complex phase vector that doesn't seem to correspond to a partition in any natural way, right? Because it just doesn't. On the other hand, algebraic connectivity gives us a way of measuring connectivity, which works for it works for any continuous vector. So we can certainly, let's say, take this vector and plug it in here. We can't turn it into a partition. So that's sort of intuition of why these things are related. But still, maybe someone smarter than me could, certainly there are many such people, could prove some relationship between complex phase retrieval and the Cheever constant. Certainly you can do it through the Cheever inequality, but it wouldn't be the same constant. So what I want to say now is that this really is not an artifact. So you can actually show that in a way this is optimal, okay? We show this at least, for an example. So in general, we have an LCC measurement scheme, and specific instantiations of this, we can show that our bounds are tight, okay? So we have phase retrieval problems on C to the power of D, with stability constant, which is bounded above and below by something which is linear in D. Okay, the bound above comes from our algebraic connectivity bound. The bound from below, I'll talk about in a minute. Okay. Similarly, for RD, we have a similar thing, right? We have this bound that's proportional to D to the half in these problems from above and below. Okay, what this is, so actually we don't have to work very hard because we already mentioned all the, in these specific examples, all the ingredients we already mentioned in a way. So the problem where we know how to show this tightness is the example we talked about before, this finite dimensional example. And we're going to talk about holeless signals in a way. So H now doesn't stand for Hilbert because we're not talking about a Hilbert space anymore, but it stands for holeless. So it's a signal in f to the power of d, where f is either real or complex, where you know that if you take any a consecutive entries, then their weight is between 1 and 2, okay, or between any two positive numbers. Right, and what's special about this a, that's where the overlap is. So that's saying that, I mean, if in the overlap we have 0, then we could have problems. This is saying that we don't have any issues. Okay, so we have our holeless signals. Then we want to look at stability of signals here. So it's going to be uniform in signals in this holeless space. And so somewhere between something per specific signal and for the whole Hilbert space. And we want to see the dependence on D, where A is fixed, and also the dependence on these fields. What happens if it's R? What happens if it's C? Okay. So of course we can use our theorem for one side. Okay. So we can, how do we use it? So we look at what is the graph that corresponds to this. So this is a sort of the graph G, which corresponds to this measurements we saw before, was a cyclic graph with, in this example, it's 4 vertices, but in general, it's D over 2A vertices. Okay. And the graph, because we're talking about holeless signals, so the graph, the weighted graph also is sort of proportional to this graph in a sense. When you measure the connectivity, the connectivity bounds you get for the Cheever constant, again, it's proportional to D to the -1. For algebraic connectivity D to the -2, we mentioned that, right? So again, it's D over 2A, but A is fixed. And that corresponds to stability constants when you plug these constants into the appropriate theorems, where the constant scales like this to the -12, then you get these stability constants. Okay, so in CD, the stability constant grows like D, and in RD, it grows like D square root of D. Okay, so that's an upper bound, right? So that's, I mean, we know that there exists such a stability constant. Maybe there could be a better one. And the tightness comes from showing just, given specific examples of signals for which we have instability, right? So the inequality is reversed with some constant alpha D, which is relatively big. We want it to be proportional in the real case to D to the half. And how do we do that? We just take F to be 1. So, fixed vector 1 with D entries. And GD is a vector which is 1 half of the time and -1 the other time. So no big deal, not a very complicated example. And you can sort of see how this works because, okay, so what is the error here, right? So you have a minimization, it's now over S1, it's over -1, 1. You're comparing the two signals, F minus G, right? And no matter if you take G to be with a plus or minus, you're going to be wrong half of the time, right? With O of 1 error. So this is sort of O of square root of D at the end of the day. H here is just L2. And on the right-hand side, what happens is you're taking a window of size A, okay? And you're only taking phaseless measurements. So that means that if I take a window here, there won't be any error here. There won't be any, this will be 0. If I take a window here, it will be the same, right? Because the signals up to multiplication by -1, they are the same. So the only place where this will get anything other than 0 is just in this hole in the middle. Okay, and so the size of this is O of 1. It sort of doesn't depend on D. It only there's one point where we break, and that's where we're going to get something bad happening. Okay, and therefore we get a constant which is proportional to D to the half. In the complex case, it turns out, so we could take GD again to be this, right? That's also a complex vector, but it turns out that you get worse the constants, which for us is better than what we're trying to prove, by just taking GD to uniformly go around S1, okay? And what this looks like, so on the right-hand side, you still get something which is proportional to O of square root of D. But on the right-hand side, it turns out that this is more confusing in a way to the phaseless measurements, because what will happen is that you get uniformly on each small segment of size A, you get a very, very small error because you're almost constant here. And you compare it to the 1 function, which is completely constant. And it turns out that that gives, if you compute it, that gives a different, a much smaller error, which actually decays with D. Okay, so anyway, that's that. So that sort of shows tightness. And I just want to brag a little bit that besides, just showing tightness of our results, this also has something sort of relevant to this specific example. So the specific example is actually relatively well studied in the last few years. People are interested in understanding how well you can do phase retrieval, and the fact that it's finite dimensional is helpful when you actually want to do an algorithm. So you can, there aren't really any algorithms in infinite dimensions, so it's easier to work in finite dimensions. And there were results in this, specifically for this model, which showed that the stability constant cannot grow better than D to the half on the one hand. And on the other hand, there are algorithms which sort of show stability constants which grow like D squared. Stability is not exactly like in our definition there, but it's very related. It's sort of saying, if you add noise of size n, then the error will grow like D squared times n. And what we show here is that the stability growth rate is exactly D. So it's sort of showing on the one hand that this bound is not as tight, and on the other hand, that you can do better from the algorithm's perspective, or at least you can hope to do better. Okay, so that's an interesting point, which I hope to also, we hope to sort of get to algorithms which actually do that in the future. And I should say that this is a certain way of, this does come from like, in the model I showed you, I take various parameters in the model in a very specific way. So it's, didn't necessarily think of it exactly like this. They have various different parameters which they don't fix as I fix, but so it's not, just to be fair to them. And now, Boris, when do you want me to end? You're muted. You're muted.
Boris, you're on mute.
You can finish at 4.
4. So 8 minutes, right?
Mm-hmm.
Okay. So that's that. Now, I'll say a little bit about an infinite dimensional example, right? So as we said, the structure was we have some theorem about LSTC measurement schemes in general. Finite dimension, we showed that we have mild growth with the dimension, right? So we know for RD, it goes like D to the half, for CD, it goes like D. At the end of the day, we didn't escape the curse of dimensionality completely, right? Because we, even after we assume that the signals don't have holes, so, when every segment of length A, they have something inside, still the stability does grow with the dimension, but it doesn't grow exponentially, it grows linearly or less than linearly even, so it's a little bit better. So then a sort of interesting question is, in infinite dimensions, let's say I have an infinite dimension LSTC measurement scheme. So can I ever get a stability, stability constant? Because it seems like, if the constant grows with the dimension, then in infinite dimensions, there won't be any constant, right? Which, in a way that's true. We'll see in a second. So for that, I'm going to go to an infinite dimensional example. Let's, for the sake of time, skip what exactly this looks like. So, this is the Hilbert space, if you can read it really, really fast. And the measurements are sampling, but for the sake of the matter, let's just assume we have some sort of infinite dimensional problem for which I can apply our theorem. And it's over the reals in this case. Okay, and so we get a stability constant from our theorems, which is proportional to the Cheeger constant, right? Now, the question is one interesting question. For infinite dimensional problems, we have infinite graphs. So how are these things related? So one thing is that the graph is connected. Second thing is that the algebraic connectivity, the second eigenvalue is larger than 0. The third is the Cheeger constant larger than 0, right? So for finite graphs, all these things are equivalent. What happens for infinite dimensional graphs? So as it turns out, this is still true, which is because the Cheeger inequality is still true. So in a way, the Cheeger inequality here is more interesting because it says that these things vanish together, while for connected, the relationship to connectivity is no longer correct. So you can only have the arrow in this direction. So if the Cheeger constant is positive, that means the graph is connected and it's sort of stably connected in a sense. But you could have a graph which is connected, an infinite graph which is connected, but whose Cheeger constant is 0. Okay, and as a result, our constant in this theorem will be infinite. Right. So the question is, at least from our perspective, what is, when can we get a positive Cheeger constant, right? And it turns out that if you look at, these are just 2 examples, but if you take signals in this space and you have a uniform exponential decay, so the signals decay exponentially with some data, then you get a positive Cheeger constant. But if the decay is polynomial, then the Cheeger constant will always be 0. So to me, it sort of complements the result before in a way, because before we saw that, even under the assumptions of holelessness, we get Cheeger constant which grows with the dimension. So here we sort of see that, often the Cheeger constant will be 0 in infinite dimensions. But it is true that, if specifically you take a uniform exponential decay, then you will get a positive Cheeger constant. But, it doesn't work, for many other examples. Okay. So
what's the dependence on beta in case 1?
Like how specific? I don't recall actually.
If it's super exponential decay, like Gaussian decay.
Don't know that either. I don't know.
Uh-huh.
I don't. I mean, we didn't go down that rabbit hole. I don't know. Maybe the shear constant goes to infinity. I don't know. Okay, so that's that. Okay, and so to recap, the results we saw were, so in general, for an LCC measurement scheme, we have these results, which inequalities which relate real stability to shear constant, complex to algebraic connectivity. In finite dimensions, we showed that we have mallet growth of the dimension for signals with no holes, and we can specifically say what that growth is. And in infinite dimensions, we have stability for monotone exponential decay, but often we don't. So that was in general that, and I'll say a little bit about future work. So two things I would like to do. One is to, so in a way I told you about this Gabor phase retrieval, which is where we started off from. Ideally, what you'd like to do is to be able to say that for Gabor phase retrieval, it's enough to take a discrete sampling, dense enough, and do stable phase retrieval if the signal F is connected. This is something that, I mean, at least we know that you can define a frame in this way. So if we don't have, if we do have the phases, you can, it is enough to sample discretely. So, you know, that would be good, but in practice, we can't do this. So we don't yet. So our methodology works for some discrete phase retrieval problems, but not the phase retrieval problem, which we sort of started out with. And another thing is to, which I mentioned before, is just to have an algorithm which actually achieves these stability rates. So d to the half in the real case and d over d in the complex case. And that was it. So thank you very much.
Okay, thank you very much for a nice talk. Are there any questions?
So if you have an infinite graph, but you have some strong bounds on the degree of the vertices, then can you regain the relation between connectivity and the Cheeger constant and the gap in the Laplacian eigenvalues? Because all the examples I can imagine are of cases where I just keep growing the degree of something, and then obviously I can have the boundary goes to 0 compared to the volume. But if I have strong bound, like, I don't know, that the degrees is limited even by a constant.
So for us, the graphs are weighted. So I guess, I mean, but I think I understand what you mean, right? So that you mean like the weights are.
Yeah, or the total weight is limited by a constant, yeah.
Right, but I mean, so let's say if we look at, so in the example where, yeah, in the polynomial example here, so would that fit with what you're asking or not? Well, there is a decay here, right?
Yeah, there is a decay, and so the sum would be bound, I think.
And this, so it is bounded, or, I mean, you can't have, it does decay, but you have to have a decay because otherwise, I mean, if you want, we want the weights to sort of to be summable. Otherwise, then, you know, you're in a whole different game, which people also have played of like, you know what, when the weights are summable, which is what we assume, then life is easier.
I see.
Yeah, because otherwise you'd have all kinds of issues. You know?
Okay, other questions?
Can you, Nadav, can you just repeat your intuition? You had this page of intuition into why the Cheeger constant is, the connectivity is the actual issue in these things.
Like with the two Gaussians over there?
What?
With the two Gaussians, the sum of Gaussians?
Yeah.
That one? This one? Yeah, so I'm saying, I mean, so when I give you an example, the question is, I mean, so specifically assume that, you know, the linear measurements here are sampling. Or it could also be the Fourier transform because it's a Gaussian, but never mind. Okay, so sampling, right? And you have a sum or a difference of, you know, the sum of these two Gaussians, that's the blue signal, or the difference, which is this yellow signal.
Right.
Right. And then I'm going to sample, say, in the peak of this Gaussian, which is certainly not the worst place to be, right? And, yeah, I want to know if I'm the yellow signal or the blue signal. So how, but I only get the phase. I don't get the phase, right? So it could be, I don't know if it's positive or negative. So the only difference between these two signals is that this is like, a Gaussian constraint here plus some tiny thing that comes from this, minus some tiny thing that comes from the other Gaussian. And this signal is, is this big Gaussian plus some tiny thing that comes from the other Gaussian. So they're almost the same, right? So if you have a little bit of noise, it will be very difficult to tell them apart. That's the intuition.
I mean, does this go further than like? It seems to me that this is just like a very simple case. So, does this really, here we're talking about two, where you have would have two disconnected components, right? If you, right?
Mm-hmm.
Is there some argument to make where
you're asking about different? Sorry. No?
Yeah, right. I think you got my.
You're asking about what if they're more connected components, or what if the signal, if you're measuring differently? Which one?
I guess I'm asking for a more general sort of insight into.
So I think so. The insight. So there's a theorem that says that you can never get stability in infinite dimensions. If you look at the proof of that theorem, so it's sort of related to, the places where it's unstable is sort of something like this. So in there you have, the measurements are in general some vectors in your Hilbert space H.
Right? Okay.
All right. And there is some sort of, given a Hilbert space and a measurement scheme, then there is some sort of notion of disconnectivity, which is related to that. So
right,
for example,
right. So really,
you can come up with a measurement scheme where these two signals are not difficult to distinguish, but that measurement scheme will have some other problem, which is related to
anomaly.
Okay.
That's